specialized in solving FE exam for civil engineers. Today I will solve several fluid mechanics and hydraulics problems. Let me share my screen. Maybe you can, Okay, question number one is about pipe flow. So we have a flow in a pipe flow, pipe flow. We know the velocity and the diameter. So the velocity is 3 meters per second. And the diameter is 0.5 meter. Now the diameter is reduced a certain distance later to 0.5 to 0.25. V2 equals 0.25 meter. So we want to determine V2. Determine the velocity after the pipe diameter is reduced. So this is a very straightforward problem. So from the first section, we know the velocity and we know the diameter. So we can determine the flow. So Q equals V A. I'm applying this to the first diameter. So A1, let's say A1, now A1 equals, or A in general equals pi B square over 4. This is the area, a circular pipe. So Q equals V, which is 3 meter per second, by A, which is pi D1.5 square over 4. So flow is 0.59 meter cube per second. So this is the flow. Now the flow in the pipe didn't change by the continuity. Flow is the same. So now we can determine the velocity in the second cross section, or in the second when the pipe diameter is reduced. So V2 equals Q divided by A2, which equals V2. Q is 0.59 divided by A, which is by D2 square, which is 0.25 square by D2 square over 4. So 4 comes here. So we have V2 equals 12 meter per second. So this is the solution. This is very straightforward problem. We determined Q from the first known velocity and diameter, and then we determined the velocity of the second when the pipeline diameter is reduced, again by applying the same formula, V equals Q over A. The next question, we have a water tank to a depth of filled of water to a depth of 3 meters. This is water surface. This is 3 meters. And we have an opening at the bottom of the tank, an orifice. Here, there's an orifice. here, and water is exiting from this orifice, and we want to determine V at the orifice. So here, in this case, we apply Bernoulli equation between a point at the water surface, 1, point 1 at the water surface, and point 2 at the orifice. Now, when applying Bernoulli equation to a fluid, a static or moving, we can apply Bernoulli equation between any 2 points within the fluid. However, we should check the points that simplify the equation, where many values are known. So here we select the water surface. Now the water surface, we know the pressure is 0 because we use gauge pressure, and we know the velocity is 0 or negligible. So these 2 terms are cancelled. That simplifies our solution. Now, whenever we apply Bernoulli equation, we have to select a datum, a reference. Again, we select the datum that simplifies our solution. So we select the datum here, or the reference at the bottom of the tank. So this is the datum. Z equals 0, the bottom of the tank. So now we apply Bernoulli equation to section 1, or point 1 and point 2. Now Z1 plus P1 square over 2G plus P1 over gamma equals Z2 plus P2 square over gamma plus V square, V2 square over 2G. Now we have Z1 is 3. Let's first cancel the zeros. Here we have Z2 is 0. We have P1 over gamma is 0 because it is atmospheric pressure, and we are using gauge pressure. P1 is 0 at the surface of the tank, or negligible, usually a very large tank. So we neglect the velocity. So we know Z1, we know P2. So P2, and we want to determine V2. So P2 at the bottom of the tank equals rho G H, which equals 1000 or 9.8 gamma for the water, 9.81 by 1000 by 3. So this is the pressure at the bottom of the tank. Now, E2 is 0 because the water exists to the atmosphere, so this is 0. E2 is also 0 because the water exists to the atmosphere. So we have also E2 is 0. So we have V2 square equals 2G C1. So we have V equals square root of 2 by 9.81 by 3. And we have V equals 7.67 meter per second. Now, in this type of problem, you can immediately apply if it is a reservoir exposed to the atmosphere and we want to find the velocity at any point downward, V equals square root of 2gh. V equals square root 2gh, where h is the depth from the water surface to the point where we want to determine the velocity. This is just to save time. Okay, so a quick equation or a quick formula, 2gh. Okay, this applies to a reservoir where there's a water surface exposed to the atmosphere, and the water also exits the atmosphere at the orifice. So you can simply apply to square root of 2gh. Next question. There is a watershed of known area, watershed. Area equals 150 kilometers square. And we know the precipitation is 800 millimeter. And the evaporation is 400 millimeter. And we want to determine annual volume. Determine runoff volume. Here we know the precipitation, the evaporation, and we want to determine the runoff volume. So the water available or rainfall available to make runoff is the precipitation minus the evaporation, and we multiply by the area to determine the volume. So the volume, runoff volume, V equals precipitation minus evaporation by the area, and we do unit convergence. So where precipitation is 800 minus 400, so that's 400 millimeter. We divide by 1,000 millimeter. This is millimeter. Here, meter. And we multiply by the area. The area is 150 square kilometer. So 150, 1 kilometer is 1,000 meter square, so by 1,000 meter. So we do the calculation and we get the volume of the runoff equals 60 million by 10 to the 6 cubic meter. Again, this is a very straightforward problem. We simply multiply the precipitation minus the evaporation. So this is the rainfall available to make runoff. And we multiply by the area, and that will give us the total volume of the runoff. Next problem. We have a water tank filled with water to a depth of 3 meters. The 3 meter, and we want to determine the pressure at the bottom of the tank. So P, this is again very straightforward. P equals rho GH. This is static pressure. Rho GH. So P equals rho, which is for the water 1000 by 9.81 by 3 meter. So P equals 29,430 Newton per meter square, which is Pascal. So this is the answer. It's very simple question, straightforward. Just P equals rho GH or gamma H. So this is the pressure at the bottom of the tank. Next problem. Again, this is about the curve number method. We have a catchment with a curve number equals 90. Catchment. We have the curve number equals 90. And we have the precipitation equals 80 millimeter. And we want to determine direct runoff, determine direct runoff using the curve number method. Now in the curve number method, there are 3 steps. So first we determine the storage. There's a formula for the storage. Then we determine the initial abstraction, which is 0.2 of the storage. Then we calculate Q. There's also a formula for the Q, which is the runoff. So step number 1, we determine the storage, determine maximum storage. So S equals 25,400 divided by the curve number minus 254. This is the curve number method to determine the storage. So storage equals 25,400 divided by the curve number, which is 90 minus 254. And that gives us storage equals 28.22 millimeter. This is the storage. Now the second step, we determine the initial abstraction. So initial abstraction equals 0.2 multiplied by the storage. This is an assumption in the curve number method. So initial abstraction equals 0.2 by 28.22, which gives us initial abstraction equals 5.64 millimeter. Now we determine the runoff, direct runoff, Q, from the following formula, which is P precipitation minus initial storage square divided by precipitation minus initial abstraction plus storage. So this is the formula for determining the runoff, direct runoff. So we have the precipitation is given 80 millimeter minus initial abstraction, which we calculated in the previous step, which is 5.64 millimeter square divided by precipitation is 80 minus 5.64 plus storage is 28.22. So if we do the math, Q equals 53.9 millimeter. So this is the answer. Now in this, when we are asked to use the curve number method, there are 3 steps. First, we determine storage, maximum storage. There's a formula for the maximum storage. Then we determine initial abstraction. Also, there's a formula for the initial abstraction, which is 0.2 of the maximum storage. And then we determine the Q from the formula for the Q, P minus initial abstraction squared over P minus initial abstraction plus storage. It's again very straightforward method. Now the next question, we have a storm precipitation equals 25 millimeter and area of the catchment equals 10 kilometers square, and the runoff coefficient C equals 0.4, and we want to determine runoff volume. Determine runoff volume. Here we simply use the direct, the rational method. So runoff volume equals the coefficient, runoff coefficient by the precipitation multiplied by the area, and we do unit conversion. So we have the runoff coefficient is 0.4 multiplied by the precipitation, 25 millimeter. We convert to meter. So we divide by 1,000 millimeter per meter. And we multiply by the area. So we have the area in kilometers square. So 10 kilometers square by 1,000 by 1,000, which is 1,000 meter per kilometer. So if we do the calculation, so we have volume equals 10,000 cubic meter. So this is the volume of the runoff all over the catchment. So this concludes our video for today. If you have any questions about the problems I solved today, you can send me a comment about the question. If you have also any question you have problem with or you need to solve, you can also send me in the comments. Thank you for following my channel, and I look forward to seeing you in the next video.